So this lecture is going to deal with the liquid state and build off our knowledge of intermolecular forces of attraction. So before we get to liquid state, I just want to show a few examples of intermolecular forces in nature, and in particular hydrogen bonding. So one of the things you may know is that proteins are highly dependent upon their structure. And we're seeing this every day of our lives right now with the coronavirus out and the spike proteins, which have a very specific structure to them. Um, so the structure of a protein is held together. So this is trying to show a protein folded in a certain way. So these long chains of amino acids. And this gives rise to the shape of the overall protein. And the shape determines function. So what maintains the shape of a protein? It's intermolecular forces of attraction. And so what you're seeing here is this long chain of amino acids that build up our protein. And what's helping hold this chain in place are these, in particular, hydrogen bonding interactions between atoms. So this is what's giving it this alpha helix, as we call it, as it twists around and being held in place. And one of the interesting things about that is it's fairly easy to destroy the structure of a protein. And so one of the ways we do this all the time is when you cook eggs. So if you happen to cook eggs, when you crack the egg and put it in a frying pan, you get a very clear egg fluid and then your yolk. This is very protein rich, and that protein is albumin for the most part. There's a bunch of proteins in there. And this is held together in its form and its structure by hydrogen bonding. And if you apply heat to this, and put it on the stove, it turns white. So what you're doing is you're destroying the structure. You are providing energy to break the hydrogen bonding and collapsing the structure of this, which now makes it insoluble and precipitating it out to get the white of the egg. And so you're denaturing your protein. So next time somebody asks, how do you want your eggs? You can just say denatured. Another example of hydrogen bonding is in DNA. So you may have learned in previous classes that when we have DNA, we have our double helix structure, and we know there's base pairs, adenine, thymine, guanine, and cytosine, right? And we also know that, A always bonds with T and G always bonds with C. But the reason for that is hydrogen bonding. So we can see with our thymine and our adenine, the reason why these bond together and they connect the rungs of our ladder of DNA is because the arrangement of the oxygen lone pair to the nitrogen hydrogen, and then the nitrogen hydrogen to the nitrogen lone pair, they match to form this nice hydrogen bond. And so the rungs of a ladder of DNA, when we talk about those rungs, are nothing more than hydrogen bonds between the base pairs. And so overall, when we have our intermolecular forces of attraction, remember these are forces of attraction between molecules. IMFs are responsible for a lot of physical properties: boiling point, melting point, surface tension, viscosity, and more. The stronger the force of attraction, the more difficult it is to separate them, which is why we can use something like boiling point as a measure of how many IMFs are present. And we said there's three types of intermolecular forces of attraction. Hydrogen bonding are the strongest, then London dispersion forces, and then dipole-dipole. So that gives a nice summary of our intermolecular forces of attraction. At this point, there's another little worksheet on Canvas. So I would encourage you to stop and complete the worksheet, additional IMF problems, and then keep going with this lecture to see how you did. So on this worksheet, the first problem you're given some data. And with this, we're sort of asked to justify the boiling point data of these three molecules: ethane, formaldehyde, and methanol. And we're given a couple pieces of information. We're given the molecular weight, right, which are all approximately the same. We're given a measure of the dipole moment, so we can see this is a nonpolar molecule. Both of these are polar molecules. And then we're given boiling point data. And so why is it that we see this trend in boiling point data? And why does methanol have the highest boiling point of all of them? And when we think about why that is, in methanol, the LDFs of all three are the same, and the dipole moment of formaldehyde is actually bigger than that of methanol. So what's the difference here? The difference is our methanol molecule has an oxygen and this hydrogen, so methanol can hydrogen bond. And that's the only one of the three that can form hydrogen bonds. So it's the ability of methanol to form a hydrogen bond that's going to give it the highest boiling point. Then, between formaldehyde and ethane, they have the same London dispersion forces, but formaldehyde is polar, which is why it's going to have the higher boiling point over ethane. In our next examples, we're given 3 pairs of molecules and asked to predict the boiling points. Which one will have the higher boiling point? In other words, which has the stronger IMFs. And so in our first pair, we have methylamine, CH3NH2, and hydrochloric acid, HCl. And what I hope the conclusion you came to was the higher boiling point has to be this CH3NH2. And the reason for that is this one can form a hydrogen bond. HCl is not capable of hydrogen bonding. It's the presence of the hydrogen bonds between molecules. It's going to make CH3NH2 the higher boiling of the two. In our second example, we're looking at the difference between 2 isomers. So what we mean by isomers, they're molecules with the same formula, but different arrangement of atoms. So that also means they have the same number and type of each atom. So the LDFs of these 2 molecules are going to be the same because they're the same number of electrons. So which is going to have the higher boiling point? And in this case, you should have come up with the fact that CH3CH2OH, ethanol, will have the higher boiling because in this case, ethanol has this OH group, and this group allows us to form hydrogen bonds. In the case of our ether, CH3OCH, it has lone pairs on oxygen, but there's no hydrogen on an oxygen to form a hydrogen bond with. So this will have the higher boiling point. In our last example, this one's a bit tricky because we have 2 molecules with the same molecular formula, same number of electrons in both cases, both nonpolar, and both can't hydrogen bond. So we might think that they have the same boiling point, but it turns out the first molecule has the higher boiling point of the 2. And the reason for that is because in this case, the molecules spread out. It's sort of like a cylindrical molecule. So in the first case, your molecular shape might look something like this. And so if you think about that, the chance for London dispersion forces would be all along the molecule like this. Kind of looks like a hamburger. In the second example, our molecule is spherical. And so in this case, because it's spherical, the shape is such that you're going to have much less chance for London dispersion forces just because the molecule can't line up and interact in the same way. So these increased London dispersion forces give rise to the higher boiling point. All right, so let's chat a little bit about the liquid state and just go over some properties. And all of these properties depend on intermolecular forces of attraction. So we can discuss the viscosity, the measure of a liquid's resistance to flow. So things that are really thick, like maple syrup, like molasses, what that's telling you is those molecules stick together a lot. So they have a very high amount of intermolecular forces of attraction. We have surface tension, the resistance of a liquid to spread out and increase its surface area. So here's a picture of mercury, which is all going to stay together. So again, these droplets are held together by molecules sticking together from intermolecular forces of attraction. And then we have capillary action. So this is when a liquid rises up a narrow tube. And we see this a lot with, this is why we measure the bottom of a meniscus in when measuring the volume of water in a graduated cylinder, because the water is creeping up the sides of our vessel through this capillary action. With that capillary action, if we looked at it a little closer, if we were to put something like mercury into a glass tube versus water, when you actually look at mercury, you actually measure the top of the meniscus because mercury bends away from the glass, whereas water bends towards the glass and starts creeping up. And the reason for that is the glass is made up of silicon oxides, so a lot of silicon and a lot of oxygens. And those oxygens provide great hydrogen bonding to water molecules. Mercury only has London dispersion forces, and so it can't interact well with the walls of the tube, so the mercury stays stuck to itself and actually avoids the surface of the glass. Water is doing the opposite. So a nice little application of IMFs in our capillary action. And then the last point we'll make on our IMFs in the liquid state is if you've ever belly flopped, you might ask yourself, why does it hurt so much when you undergo that belly flop? As you jump down and splash into the pool, why does that hurt so much? And so the reason for that is when you jump down and land in a pool of water, all of that water on the surface is being held together by intermolecular forces of attraction. So when you slap that water and push it all out of the way, you have to overcome all of those hydrogen bonds. You have to physically separate molecules of water, and that takes a lot of energy. And so water is a small molecule, and being a small molecule, it means there's a lot of water molecules that would be in the surface of your body. And it can hydrogen bond so well that it's just so much energy to do. And in fact, if you've ever watched people practice diving in a pool, one of the things they do is they have a bubbler and they just send bubbles up to the surface of the water. And the point of that is to agitate the surface so the hydrogen bonds are being broken for you so that when you jump in, it's not going to hurt because the surface tension is already destroyed. So if you are learning to dive and don't know how to do it correctly, even if you belly flop, it's going to hurt a lot less because that surface tension has been destroyed. Thank you.